Imagine you're designing a high-performance CPU, and you need to optimize the cache hierarchy. You've probably heard of L1 and L2 caches, but what about L3 cache? Let me show you a little-known trick to power down this crucial component. Most CPU designs use L3 cache as a shared resource for each core. However, when a core is idling or in power cycled mode, we can save precious power by disabling the L3 cache entry. This is where the cache power gating (CPG) technique comes in, allowing us to dynamically shut down L3 cache access when necessary. But here's the catch: how do we actually control CPG in modern CPU designs? It's not as simple as flipping a switch, as we need to consider the overhead of cache flushes and power-up sequences. That's where the exclusion principle comes in, by mandating each core to flush its own cache entries before disabling L3 cache access. Now that we've covered the theory, let's talk implementation. In real-world designs, we'd implement CPG using a combination of hardware and software mechanisms. This could involve hardware registers that track cache access and power states, as well as software code that manages the L3 cache exclude mechanism. During power-down sequences, the system would temporarily stash the last loaded instruction in a special register, allowing the CPU to quickly recover to a known state. This technique requires careful consideration of latency, power consumption, and performance overhead, all critical factors in modern CPU designs. So why is CPG not more commonly used? One reason lies in the challenge of integrating this complex logic within the CPU's already crowded design space. As system designers, we must navigate a fine balance between power savings, performance, and implementation complexity. Now let's explore the practical implications of CPG. By optimizing power consumption during idle periods, we can significantly reduce overall system power draw. This translates to longer battery life in mobile devices, lower energy costs in data centers, and reduced heat dissipation in high-performance systems. From a software perspective, we'd need to update our code to manage L3 cache access and power states correctly. This involves rewriting critical system calls to leverage the exclusion principle and properly handle cache flushes, all while minimizing the impact on system performance. As we close, remember that optimizing CPU power consumption requires a deep understanding of complex interactions between hardware, software, and system design. CPG is just one example of the many innovative techniques available to system designers, engineers, and developers seeking to push the boundaries of performance and efficiency. Thanks for joining me today as we explored the world of cache power gating. If you're interested in learning more about cutting-edge computing techniques, be sure to like and subscribe to our channel for more in-depth analysis and expert insights.